First, I'm going to talk about GPR. So a ground penetrating radar system is made up of two antennas. You've got a transmitter and a receiver. It's going to send an electromagnetic pulse, a radio wave, into the ground, and then the receiver reads that pulse as it's reflected back up. A digital data logger on a computer will record the reflected signal, and it will also record the travel time and location. So different GPR systems can look different. Some of them look like this, like a little push cart. This is the one that we have, one of the ones that we have at IUP, and the one that we use most often. It is quite literally a modified jogging stroller. The company that manufactures it, GCHS, had an agreement with the stroller manufacturer. So like, it even has a little footrest on it that says "Don't stand on me." But as the data is collected, the speed of that pulse moving and the subsurface material are correlated to the interpretation of that. So, in other words, when you know what the ground is going to be made up of, and you know how fast that signal is moving, you can use those two things to calculate how deep those anomalies are. And when you're stitching data together, you can produce a 3D model of the subsurface. Not all materials are suitable for GPR. One of the biggest challenges in collecting GPR data is attenuation, which is just a fun word for how much the signal is being lost as it travels through the ground. Higher attenuation means worse results. So materials that have the lowest attenuation are going to be dry sand, wet sand, air, non-salt water, both freshwater and brackish water, granite, dry salt, ice. All of these things are excellent, have very low attenuation rates. Pretty medium, you're going to have your silts, your shells, your clay. So it's very useful in environments like Pennsylvania. You're generally not going to find it being used in seawater. Salt water has very high attenuation, so it's not super useful. At this site in particular, most of the soils are silt loams, and there's some silty clay loam. So it's a pretty well-suited medium attenuation. And you tell the GPR what attenuation rate you're expecting. And so it's going to use that and the speed of the signal as it's read to calculate that for you. GPR surveys are usually done in defined survey grids with defined transect spacing. So for this project, we did a 20 meter by 20 meter square as our initial survey grid. This is just one of the lines marking the edge of the initial grid. We want to have some overlap in the data we're collecting so that we can capture greater detail. And it's important to note that the signal actually moves conically. So it's not going straight down, it's going out in a triangular shape. And that means you don't have to be right next to each other to get some overlap. Depending on how deep you're targeting, you can have broader spacing, or depending on how much detail you need. Generally, the best practice that I was taught is to hit targeted anomalies at least 3 times so you can have as much detail as possible. We have, in this area, it's highly disturbed, and it's on the opposite side of the chapel from the church's historical cemetery. But both the priest and I were particularly concerned about the chance of identifying an unmarked grave, and keeping that in mind, we chose 25 centimeter spacing, because even if you're catching a grave on the short way, you're going to hit it 3 to 4 times. That would just give us very clear detail for anything that is suspiciously shaped like a burial to avoid unmarked later. We collected data unidirectionally where possible, so always moving in the same direction, making data a little bit easier to process. But because of some obstructions in the field, which I'll talk a little bit more about later, we did do what are called reversals. We went the opposite way, where we had to collect more data. Some of these are all lovely obstructions in the field, beautiful landscaping, not so beautiful. So the picture on the left here is a little silly, but it shows part of the challenge of navigating a GPR system on different terrain. We use a GSSI SIR 4000 system with a 400 megahertz antenna. It's mounted on a utility cart with a distance encoder on one of the rear wheels. That lets the system calculate the distance it's moving. The company, like I said, manufactured these parts in agreement with the stroller manufacturer. So it's basically a modified stroller, which makes it very easy to push over smooth terrain. But if you ever push a stroller over anything that's not smooth, you know it's pretty terrible. So that picture does not do justice how steep the edge of the church lawn is right there, which makes it a little bit difficult to steer. And otherwise, the ground was well suited to a survey. And I've spent an entire day clearing brush in a marsh to do a GPR survey, so this was much nicer than that. It could have been much worse. And then, like I said before, this photo on the right just shows one one edge of the initial survey grid. To move in a straight line for GPR, the practice that we use at IUP at least is using cones. We have a measuring tape on each of the sides that we're moving from and towards, just for collecting data in one direction. And we use a cone to sight a nice straight line going down and move them down so that we know where we're going. One of my favorite useless skills is my now very well known ability to walk in a perfectly straight line. Not that anyone's testing. The other method that I used for this project was a magnetic radiometer survey. So magnetometry measures the ambient magnetism of objects below the tool. And luckily for us, archaeological features often have magnetism that is distinct from the surrounding matrix. When we say magnetism, we usually think about magnetic objects, but that's only one piece of the puzzle here. You don't have to be magnetic like a nail or a piece of other metal to have magnetism. The magnetism of an object can be affected by many things. For example, bricks have magnetism as a result of their fire, and rocks have magnetism as a result of the direction or the alignment of Earth's magnetic field whenever they're first formed. And since we're looking for anomalies, whenever we're scanning the magnetic field of the area, things that are like rocks that have been moved or bricks that have been fired are going to show up as anomalies. So a magnetometer survey like this can be great for identifying structural remains at mine site. We used a Geometrics G864 CCM magnetometer in gradiometer configuration. So the photo is on the right. It looks kind of like the tool from the Ghostbusters, and it is much harder to carry than it looks. It's basically a very large backpack with the long pole mounted. It has a shoulder piece to keep the weight up, but you want to keep it perfectly straight as you're moving. In this case, with a gradiometer, you just have two stacked magnetometers. The one on the bottom is reading magnetism at the Earth's surface and below it, and the one on top is just reading that magnetism at the Earth's surface. So in post-processing, we can subtract those two readings and get a sense of just what's below the Earth's surface. We collected data on half-meter transects, so a little bit wider spacing here. And unlike the GPR, where we sight it with a cone and walk in a very straight line, this tool, it looks deceiving, but it is much harder to steer than the stroller is. So we actually place a non-magnetic tape down to guide the tool on each transect. So those are the tools that we use and a little bit about how they work and how you collect data with them. I'm going to talk about how we selected the location for the initial survey. So this is the church property in 1901. You can see here, we have a picture of the chapel, the cemetery in the back. This is Mark's Vineyard and Orchard. This bar is still standing across the street. And this is what we use as a base to try to figure out where that school building might be. There's a little square right here marked SCH. And based on that and photos, why we can assume that building is probably the school, but we're going to investigate it further. This was the starting point for figuring out where to place the grid. The original school was demolished, but also since then, they've built the new school, they've expanded the parking lot, and built out a new parking lot in front of the residence and the new school building. The road out front was also expanded. And so I took this map and I brought it into ArcGIS. On the left is just a cut version of that map showing you just the chapel building and the front lawn. And on the right is what that looks like brought into ArcGIS. Like I said, the landscape and the roads have changed a lot. So to georeference this and kind of stretch it to fit the modern landscape, I relied a lot on the church building itself, knowing that that hasn't moved. It's grown, but not the base of it. And also some of the intersections to the rear of the property, kind of on like the northeast side, have stayed very similar. By georeferencing that map, you're able to get a sense of where that building might be. And you can kind of see through here, it's right on the corner of the church lawn, straddling into this road called Basilica Drive and into the parking lot for the school. The other benefit of this is that it gives us a sense of the size of the school. Because we don't have any complete photos of it, by doing this, we're able to measure it, and it's basically a 30-foot by 30-foot square, which gives us a sense of what size of anomaly we're looking for if there are structural remains associated with the building. So, having done that, this red square on this map is an estimated footprint of the school based on that map. And I placed an initial survey grid in Archaeological just to get an idea of if we could place a 20 by 20 meter grid with avoiding some of the obstructions. So right here, we have the row of parking means and all of those. This is a brick lined garden bed that has a bunch of bushes. We've got a tree right here with a metal stake that can't be pulled out. And over here is a very steep edge of the church lawn that goes right up against a retaining wall. So placing the grid, we ended up moving it around a little bit. This was just to get an idea to see if that size of grid would be possible while limiting some of those obstructions. And also just to note, in addition to all of our geophysical methods in the field, we took GPS points of the corners of the grid as placed in reality, and also all of the obstructions that we had. That way, if we had any data that was missing in our final process data, or anything that looked really weird, like a really magnetic spot in the middle of the field, you might be able to put those GPS points over it and see, oh yeah, there's a giant metal stake that's concreted into the ground here. That will also let us bring the data into Archaeological later to collect GPS points for any anomalies that we identify in the data, so that we can go out and demonstrate them. And then just to recap a little bit the geophysical equipment that we use. This is our GPR, the GSSI SIR 4000, 400 megahertz antenna on the utility part with a distance encoder. That is our geometric magnetometer, and we also use a true GeoX gauge as our GPS in the field. The use of multiple survey methods in a geophysical survey lets you strengthen the identification of an anomaly, and it can also aid in the interpretation of the survey results. And again, to give credit where credit is due, all of the equipment used for the survey is owned by and was loaned out by the University of Pennsylvania from the Department of